Good evening. Welcome to the live session of chemistry for engineering students. I've had a live session already, but that was when we had finished our discussion on quantum chemistry, but had not started our discussion of molecular spectroscopy. Now that our part is completely complete, uh, we'd like to discuss mainly molecular spectroscopy today. But in case there are questions about the previous quantum chemistry part as well, I'd be happy to answer them. Let us go to the slides and let me show you the slides and begin a recap of the spectroscopy that we have discussed in this course. Meanwhile, if you have questions, please write them in the chat box. I'll be happy to answer them if I can. We have talked about spectroscopy of three different kinds. Microwave spectroscopy, which operates in the energy regime of rotation of molecules. Infrared spectroscopy, which covers molecular vibrations. And electronic spectroscopy, which involves transitions between electronic levels. So UV visible spectroscopy is another word for it. And in electronic spectroscopy, we talked about absorption as well as emission. The first kind of spectroscopy that we discussed was microwave spectroscopy. We discussed that for a diatomic molecule, it has to be dipolar in order to be microwave active. If it is a homonuclear diatomic molecule like dihydrogen, then you cannot see the microwave spectrum of such a molecule. But you can see the microwave spectrum of HCl, for example. And to explain the rotational spectra, the easiest model, the simplest model that one can use is the rigid rotor model, where the molecule is considered to be like a rod that rotates without any change in length. So the bond length remains constant during rotation. That is the assumption. And even then, it is a two-body problem. So it is simplified and made a one-body problem in which the mass of the two atoms is replaced by their reduced mass. And the way I remember reduced mass is 1 by mu equal to 1 by m1 plus m1 by m2. And it is considered to rotate around a massless center with a radius of r0, where r0 is the radius of variation. For this system, one can write Schrodinger equation. The Hamiltonian is going to be in theta and phi. That part of the Schrodinger equation is pretty much like what we had already for hydrogen atom. Wave functions, naturally, are the same spherical harmonics that we got from the angular part of Schrodinger equation for hydrogen atom. And when we solve this, we get the expression for energy Ej equal to h square by 8 pi square I multiplied by j into j plus 1 in joule, where j, 0, 1, 2, etc. represents the rotational quantum number. It is equivalent to the secondary or subsidiary quantum number or azimuthal quantum number L in hydrogen atom. Next, we converted this to centimeter inverse, because that is the convention that we use always. We use centimeter inverse wave number and not energy in joule when we talk about microwave and IR spectra usually. And we introduce the selection rule without derivation. The selection rule is delta J equal to plus minus 1. So a transition can only take place between rotational levels that are next to each other in energy. It cannot take place from one rotational level to another level that is away by 2 or 3 quanta. It's very easy to calculate the energy associated with it. In terms of centimeter inverse, it turns out to be 2b into j plus 1 for a j to j plus 1 transition, where b is given by h by 8 pi square IC, and it's called the rotational constant. And the good thing about this is that if you look at the energy manifold of the rotational spectrum, then you can work out the energy differences and you can work out the energies of transition. And we learned that in the microwave spectrum that we thus get, lines are separated by amounts of 2B. Welcome back, Quinoline. Welcome to all those who might have joined by now. Please write your question in the chat box. We are going to answer them as and when we reach the relevant part of the presentation. Please keep writing the questions and don't wait for me to stop. There is a time lag. I'll come to your question in due course, but whatever you ask will be answered if I know the answer, of course. Alright, so rotational spectral lines are all equally spaced for a rigid rotor, and if you look at those rotational spectra, then simply from the separation we can work out B, and hence we can work out the we'll go back a little bit maybe. So if you work out B, then what we can work out is 8 pi square IC, so I. H is known, pi is known, C is known, I. And I essentially is mu R0 square. Mu is something that you know if you know the composition. So R0 is the bond length, that is what we get. Alright. So that is one part, one aspect of the spectrum. The other aspect of the spectrum is the y-axis, intensity. The spectral lines, as we have drawn them, go through a maximum. Why do they go through a maximum? Because intensity of spectral line depends on the population of each of the levels, and each level is has a degeneracy of 2j plus 1. If you go back to the hydrogen atom problem, we'll remember the magnetic quantum numbers. So the number 2j plus 1 comes because there are 2j plus 1 number of orientations in which the angular momentum can be. So 2j plus 1 number of z components, that gives us the degeneracy. So like this. So Boltzmann distribution is Nj proportional to Gj, where Gj is the degeneracy of the jth level, multiplied by e to the power minus epsilon j by kt. So when we work with this was your homework. You can work out the value of j for which the population is maximum by simply taking the first derivative and equating it to 0. Alright. So as we said already, from B we find out the bond length, and since we started with what Max Planck had said about experimental spectra, experimental results being the only truth, we showed you an actual microwave spectrum of carbon monoxide. We talked about a few applications. Next we moved on to vibrational spectroscopy, and there we said that from vibrational spectroscopy one can determine bond strength, like one can determine bond length from rotational spectroscopy. So the basic assumption in the simplest model that we use for molecular vibrations is the harmonic oscillator approximation. We consider that the bond behaves like a spring that follows Hooke's law. So we get a parabolic potential, we use the boundary conditions, we talked about, we did not derive anything here, but we showed you what the rotational wave functions look like. We told you that the energy expression for the vth vibrational level is EV equal to V plus half h cross nu. So the lowest vibrational level, since it's V equal to 0, it turns out that it has a non-zero energy, and that energy is called 0 point energy, and it's given by half h cross omega. And this omega, of course, is angular frequency of vibration. But then we arrived at a little amusing result, and amusing for me at least, I don't know about you, where it turns out that the frequency of vibration is exactly equal to the frequency of light that is absorbed for transition from one vibrational level to the next. And in fact, the selection rule is delta V equal to plus minus 1, very similar to the selection rule for rigid rotor. And that is why only those frequencies of light are absorbed that match the frequency of vibration of the molecule. So for a harmonic oscillator, diatomic molecule, you expect a single line. We showed you a high resolution spectrum of HCl, and we found that the single line actually comprises several smaller lines, which are distributed on the two sides. When I say two sides, I mean higher energy and lower energy side of the energy gap between V equal to 0 and V equal to 1. These are called vibrational spectrum, and this fine structure arises due to the involvement of the rotational sublevels. And if you look at any of these lines, it is actually made up of two lines, because we are talking about HCl here. As we know, chlorine is present in two different isotopes, 35, chlorine 35 and chlorine 37. So these two lines are characteristic of the two isotopes. Having discussed molecular rotation and molecular vibration, we went on to electronic spectroscopy. We discussed the simple case of formaldehyde, and in formaldehyde we said we are going to talk about the pi star n pi star transitions involving the CO. So we drew the molecular orbitals, well, we depicted the molecular orbitals rather. The energies of molecular orbitals, lowest energy would be pi, then pi star, and in between you would have the non-bonding orbitals, which are essentially the atomic orbitals of oxygen, you can think, which house the lone pairs. So this is the electron configuration. The non-bonding orbital is HOMO, the pi bonding orbital is HOMO -1, pi star anti-bonding orbital is LUMO. Ground state is singlet here. Ground state is singlet here because in the simple discussion that we are doing, all electrons are paired. You have a pair of electrons in the bonding pi MO and another pair of electrons in the non-bonding orbital on oxygen. All electrons are paired. So capital S, which is the sum of all the electron spins, is equal to 0. So 2s plus 1 multiplicity is equal to 1. So singlet ground state. For oxygen, as Kunalin has asked, the ground state is actually triplet. You can call it T0, no problem. Why is it triplet? If you want to take the simplistic approach that we have taken here, all you have to do is you have to write the electron configuration of oxygen. And you'll find that you have these degenerate levels as HOMO, and you have 2 electrons there. So you have 2 electrons, one in each of these degenerate pi MOs. So again, if you take plus half and plus half as their spins, then half plus half is 1, 2 into 1 is 2, plus 1 is 3. That is your triplet state. If you want to talk in terms of spin wave functions, then the discussion becomes a little more involved. I think we have by and large avoided it in this course, so we'll not get into that today. So yes, the ground state of oxygen you can say is T0. I have put the cart before the horse a little bit because in the slide we have actually come to that discussion a little later. So what we said is that the way we have drawn it there, 2 electrons in pi, 2 electrons in n, that denotes an electronic state of S0, the lowest energy singlet state. So in the next level that we have, we can think that we promote an electron, maybe by shining it with light if it is absorbed, from HOMO to LUMO, ending up this kind of configuration. Pi 2, N1, pi star 1. And now there can be 2 situations actually. You can get singlet if the electrons are still paired, and if in any case it's called an n pi star state. So the transition that we have shown there essentially can be shown in this kind of diagram also. The other thing that can happen is that you can have transition with a with this kind, you can have a transition from HOMO -1 to LUMO. So that will give us the configuration of pi 1, N2, pi star 1. That will take you to S2. This is called a pi star state because it has addition out of S0 to S2. Sorry, it has addition out of pi to pi star transition. Alright. And the other n pi star transition that we have talked about already takes place without spin flip. That gives you the T1 n pi star state. So it's important to understand that S1 and T1 are n pi star states. S2 is pi star state. We have a couple of questions, so let's take them. Can you please show the Laporte selection rule using Jablonski diagram? Yes, you can. Even in Laporte selection rule, what you need to show is these singlet and triplet states. And the only thing that you'll need to know is what are the symmetries of the states. Laporte selection rule is something that arises out of symmetry, but I think we have that related discussion coming up. We'll come to that. Atomic spectroscopy versus molecular spectroscopy. We have not really discussed atomic spectroscopy here, but it is pretty much the same. Zeeman effect, anomalous Zeeman effect, Pascal-Beck effect, Stark effect, we have not discussed in this course. If you are interested, please see the course by Professor Naresh Patwari on quantum chemistry and spectroscopy. I believe he has discussed it there. Okay. Now, before we talk, answer the question whether T1 to T0 radiative transition possible or not, let us just talk about that. The spin selection rule is delta is equal to 0. That means you cannot, it forbids the transition between states with different spins. So, S0 to T1 absorption or T1 to S0 emission, they are actually not allowed. Orbital selection rule involves, as I started saying, symmetry of spatial wave functions. So, because of that, S0 to S1 is actually not allowed in formaldehyde. Right? We have not talked too much about symmetry, but I see that people at least who are here, Pinoli and Pashupatinath, you have taken the symmetry course as well apparently. So, you can refer to that course and you will understand. Okay. Before we go down to breakdown, maybe you can answer the next question. Is T1 to T0 radiative transition possible? It is spin allowed, yes. Is it symmetry allowed? That is what you have to see. Okay. Now, selection rules are actually things that can be relaxed to give us what are called partially allowed transitions. Spin selection rule can be relaxed by what is called spin orbit coupling, which leads to wave functions that are not purely singlet or purely triplet. Of course, when we talk about singlet and triplet, we are talking about two electron systems. And orbital selection rules are relaxed by vibronic coupling. It is easier to relax orbital selection rules than spin selection rules. So, you often see transitions that are orbitally forbidden but vibronically allowed, and it is less common to see spin forbidden transition. You do see them, but their intensities are less. When we talk about intensity, we mean molar extinction coefficient. We derived, we saw how to do it. I think it's there in the next slide. We derived your Lambert-Beer's law. I am not going to do the derivation all over again, but suffice to say that for fully allowed transition, you get an epsilon value of 10 to the power 3 to 10 to the power 5. For spin allowed orbitally forbidden transition, we get 10 to the power 0 to 10 to the power 3. For orbitally allowed spin forbidden transition, you get very small epsilon values of 10 to the power minus 5 to 10 to the power 0, but really very small. T1 to S0 radiative transition is called phosphorescence. What about S1 to T0 radiative transition? If there is a T0, it would be called a phosphorescence as well. Of course, we have not reached there yet, we will come. So then we talked about solvent effect. We explained how upon protonation n pi star vanishes, because after all the lone pair is engaged by the proton that comes in. Even if you have a polar solvent, essentially this is what we expect. You have a blue shift for n pi star transition, you have a small red shift for pi star transition, and that is something that can be explained in the energy diagram that I have drawn already. Another kind of transition that one can get is charge transfer. When you have two moieties, one electron donor, one electron acceptor, upon excitation, the electron can actually go from the HOMO of the donor to the LUMO of the orbital. Okay. Microcanonical ensemble, canonical ensemble, grand canonical ensemble are things that one discusses while talking about statistical mechanics. We have not discussed statistical mechanics in this course. Please restrict your questions to what we have discussed in this particular course. If you are interested in statistical mechanics, there is an outstanding course by Professor Biman Bakshi available on YouTube, same NPTEL course. I request you to please refer to that one. And these are all definitions of microcanonical ensemble, etc. These are all like textbook definitions. I think you can find them there. Alright, so charge transfer transition. So naturally, these transitions take place only when the energy gap is small. And there is no question of vibration or anything here. And depending on acceptor moieties can be in the same molecule. Then we have intramolecular charge transfer. They can be in different molecules. That makes it intermolecular charge transfer. And the second molecule might as well be a solvent. Then you can have charge transfer with the solvent. In metal ion complexes, you can have electron transfer, charge transfer from the ligand to the metal or metal to the ligand. I believe most of us would have at least encountered these terms in our earlier courses. And this is a typical depiction of a charge transfer band, broader and redshifted than the absorption bands of donor as well as acceptor. Next, we talked a little bit about structured absorption spectrum. We said that Franck-Condon principle in its simple form says that the transitions are vertical, classical form actually. So no internuclear rearrangement takes place during electronic transition. And the intensity of transition is given by the Franck-Condon factor. Let me try to answer Quinolin's question and we'll come back to it. Do S2P transition mean spherical electron clouds converting to dumbbell shaped? You can think that way, yes. But the only thing that I'd like to say once again here is, please remember what orbitals are. Orbitals are actually wave functions. So yes, I mean, you can talk about probability distribution. The shape of it changes. You can think of it like that. All right. Next, we discussed the different cases where we have the bond length in the excited state equal to, greater than, or less than the bond length in the ground state. Depending on that, we can have different transitions that would assume the greatest intensity. That comes from Franck-Condon factor, overlap of the vibrational wave functions. And we also defined band origin. Band origin is the 0 dash transition. Why aren't n? I didn't understand the question, Pinoli. What is the meaning of why aren't n? Please elaborate, then perhaps we can try to answer. All right, we'll just go ahead. So, if you want to read this part, I'm sure I said it during the lectures. You can read it from Atkins Physical Chemistry, or you can read it from Banwell and McCash's book on molecular spectroscopy. One interesting thing that happens is that if the bond length in the excited state is significantly longer than the bond length in the ground state, then some transitions can actually take it to the dissociation limit. And then you are going to have discrete lines followed by a continuum. And the energy at which that continuum begins is called the dissociation limit, which means excitation beyond that energy is going to lead to dissociation of the, well, we are talking about diatomic molecules at the moment. And you can have two different things here. You can have direct transition, you can have two more different kinds of things. You can have direct transitions to a dissociative state, a state that does not have a minimum, or you can have this dissociative state overlapping with an associative state. So when you excite to appropriate vibrational levels of the bound excited state, electronic state, there can be a transition to the dissociative state. We said that this forms the basis of the Nobel Prize winning experiment by late Professor Ahmed Soel, who used this to show how much time it takes for the bond to break, and not only that, how exactly the bond breaks. The last part of the course, we talked about the fate of the electronic states. We excite it, fine, it can dissociate. If it doesn't dissociate, then the molecule has to come back to the ground state and the energy has to be released. It is not necessary that the energy is always released in the form of light. If it does, then we have fluorescence and phosphorescence, and you have this kind of a situation where you see your system glowing. This is your Jablonski diagram. You have already answered a question on this, I believe. And we talked about Kasha's rule, and we said, why is it that the emission spectrum, fluorescence spectrum, is expected to be a mirror image of the absorption spectrum. But thankfully, that is not all that happens. Molecules have a different different electron configuration in the excited state. And if you have questions, please ask in the next couple of minutes, because we are nearing the end of our discussion now. And if there is an excited state process, then it is usually characterized by a redshifted emission spectrum. Of course, it is not necessary that the second fluorescence band is present, but then usually the locally excited state is non-fluorescent. And sometimes the opposite happens and you only see the Stokes shifted peak. Okay. We discussed photoacidity and photobasicity. We will not get into that discussion today unless there is a particular question. But the point we tried to make was that organic acids, aromatic acids, are more acidic in their electronic excited states, and organic bases are more basic, essentially because the electron configurations are different. We took the example of beta-naphthol and we drew your attention to the fact that this is a very, very non-trivial effect. pKa for beta-naphthol in ground state is 9.2, that in the excited state is 2. 9.2 to 2 is equivalent to a change in 7 orders of magnitude of hydrogen ion concentration. Very, very major effect. And then we briefly introduced you to other kinds of excited state process without talking about it in much detail. We talked about photoisomerization. You have a double bond which comprises of a sigma bond and a pi bond. If you do a pi-pi star excitation, then the pi bond order is 0. So the single bond becomes, the double bond becomes a single bond in the excited state. And then it can rotate. Cis can become trans, trans can become cis. That is photoisomerization, a very important process that helps us see and also helps things like bacteriorhodopsin pump protons through membrane. Another important excited process is photoinduced charge transfer. So we have talked about charge transfer in absorption spectrum. Here, this is charge transfer post-excitation. Again, the donor and acceptor can be within the same molecule. If that is the case, then these molecules are, the fluorescence of these molecules is usually very strongly dependent on the polarity of the medium, and hence one can make things like protein probes with them, or it can be intermolecular, and that is what is used in construction of things like dye-sensitized solar cells, among other things. And I think the last topic that we discussed was intersystem crossing, where excitation to a singlet state, we are talking about regular organic molecules where the ground state is singlet, can be followed by an intersystem crossing that arises out of a spin orbit mixing. Why aren't singlet and triplet energy levels stacked in one column in Jablonski diagram? It would be impossible to make out one from the other if you did that. It is done so that we can actually see that see them apart from each other. There's no other reason. It is not as if singlet and triplet excited states are in different parts of the molecule or different parts of the cuvette or something. It's not like that. It is drawn that way so that we can, so that the diagram is neater and we can make sense of them. Right. So, in conclusion, we have in this course, in our part of the course, introduced you to quantum mechanics, looked at some applications in chemistry, and finally, we have talked about quantum mechanics in action, which is some variants of molecular spectroscopy. So that brings us to the end of what I wanted to say, and meanwhile I have been hopefully able to answer the questions of these two, Prof. Bhutinath and Quinolin. I am really impressed that you have attended both the courses that offered this semester. Thank you very much. Pushpati and Quinolin and others who have taken this course may not be present here today. I hope, along with my colleagues Arnab, Chidambar and Devabrata, I sincerely hope that the course is going to be of use to especially first year students and others who want to perhaps brush up on these concepts. I understand that this course is going to run possibly every semester. I hope that this is going to be of use to a large number of students across institutes in India and maybe abroad. Let me end this live session, but before that, are there infinite singlet and triplet states? In principle, yes. Vinodin has asked, are there infinite numbers of singlet and triplet states? In principle, yes. But what happens is, generally, when you go to higher energies, the energy gaps keep decreasing. So you end up having a continuum of states. You might think of this Rydberg states. That is what you get eventually if you go to very high energy. All right. With that, if there are more questions, we'll be happy to answer them. If you can share them on the forum or send us an email or something. Thank you, everybody. Let me conclude this session by thanking the TAs. It's not been easy for the TAs because it's a course that spans lots of different areas of chemistry. I'd like to thank the NPTEL staff, Tushar, Ravi and others. I'd like to thank Bharati Tari, Bharati Satpal of NPTEL IIT Bombay. They have been, without them, this show would not have actually taken off. I'd also like to thank NPTEL IIT Madras for having coordinated not only this course, but all the courses together. Thank you, everybody. Enjoy the rest of the evening. All the best to everyone. Bye-bye.